I'll go let Carlos on that.
Alright, video panel.
Years.
Okay. So, hi guys, we're back in calculus. And we've learned about definition of a limit, both in the finite case, meaning the limit is a finite real number, and both in the infinite case, meaning the limit is infinity. I did not write the definition for minus infinity, but it's quite similar. And I will not, if we use it, I will just use it, I won't write it formally. And I left you, if I remember correctly, with a question. Yes, this one. You didn't have to answer it. I will start the day by tending to it. Just a second. Full screen. Hide video panel. Okay. And what is the class number today? 5. Class 5. Okay. So the theorem is that if AN, a sequence AN, tends to infinity, and I'll remind you what does it mean. It means that any given number, even if it's huge, like a million in the power of a million, there exists some index that after that index, all of the sequences past this huge number. That's the definition of tending to infinity. And the claim here in this theorem is that if AN tends to infinity, then its inverse, the sequence of the inverse numbers, right? If the first sequence is 1, 2, 3, 4, then this sequence is 1, half, third, and so forth, will tend to 0. It's quite intuitive, but because we had the definition, an exact mathematical definition of what does it mean to tend to infinity, and what does it mean to tend to 0, then it's a mathematical claim that must be proven. Not everything that ought to be proven we will prove in general. It's important to understand what's a definition and what's a proposition that one needs to make sure is true. So this must be proven, and in this case, we'll also prove it. In general, I'll remind you, remember the following link, https calc1mathwiki.com, which contain most theorem and propositions we will learn. So it helps you, click on it, it will help you to study ahead for class if you wish. Sometimes I will skip something and I say you can watch there, see there if you like. I will use it a bit. It's in Hebrew, that's the problem, but so I won't use it too much. And this is for later, but these are all tests of the course. It will help you to study to the test when time comes. But here, if you look, this is the first chapter. The material is all there in video, but in Hebrew. Okay, so the videos are the full material. But even without looking at the videos, just reading these short notes here, you can see certain important middle points. I had a word for it, but I lost it. Again. How do you call an important point on the road?
A key. I don't know.
Key points.
I know what you're trying to say.
Yeah. Milestone. Oh, yeah, okay. I was thinking of stones. I say, why am I thinking of stones? Am I building something? It's a milestone. Okay. Yeah. My brain. So it looks like, for instance, square root of 2 is not rational. We talked about it. A few words about powers. I'm not sure we talked about it that much, but a bit we did. Logarithms. I'm pretty sure I didn't mention all this year. And then this is the kind of the start, but you are expected to know it. These are the chasamim, boundaries. We did talk about it, and wait. Okay, so this is the definition of a limit for a finite limit, a real number. And this is the definition of a limit for infinity. And that's where I was going to. And now you look, the first proposition, if n goes to infinity, 1 over n goes to 0, right? The next will be, I'll speak about it next. But you can see here a bunch of claims. Some of them I will quote and don't prove, and if someone wish to do it as an exercise or see the video in order to do Ulpan, you're welcome to it. Always, if you feel like you need to go through a certain thing, say, I've seen this theorem, but I didn't understand it. Oh, please do it in the class. I will gladly do it because I'm not doing everything. My point is, you have to be able to prove some of these in order to understand how one proves such theorem. But proving all of them is sometimes too much of an overkill for its purpose. So I skip some of them quite arbitrarily. But knowing them, that you will have to do. I will mention all these claims because each and every one of them is important. And that's what will happen for a few lessons now, because as I said, last time I think, one of the times, calculating limits, understanding limits is, I don't know, a third of the course. It's one of the main things we study at Calculus 1, understanding the concept of limits. And I try to show you historically why is that important, and that's it. So that would be the next. I wish to be succinct in order to get across my point. Last time we did unnecessary exercises when we proved, not this one. When we proved, for instance, that 1 over log n tends to 0. Okay. When calculating limits, we won't use the definition, we won't see epsilon. That's not the way it's being done. Why do we need the definition? In order to prove general theorems, such as the one which is the first one, that's why I'm making all this noise about, such as if any sequence goes to infinity, then the sequence of the inverse numbers must tend to 0. That's such a first theorem. Let's look at another one here. If any sequence tends to LA, limit A, and any other sequence tends to limit B, then the sequence of the sum of the elements tends to limit A plus limit B. So we use these theorems when we're calculating limits easily. But in order to prove that it is generally the case, we must understand the definition. So that will be our work for a while, building theorems, arithmetics of limits in order to use it and calculate limits easily, technically later on. Okay, so now we're starting it for some time. So now proof of the theorem above. Okay, so what I know is data, נתונים, an tends to infinity. And target 1 over an excuse me?
Would it do it just like the that they that's with epsilon?
With yeah, so okay. So the data is what given to me is the limit to infinity. That means roughly that the elements of an are as big as I like, right? Roughly. What I need to prove is that. And one of the main thing about math and main thing that students always confuse, you have to have your eyes on the prize. You need to look at the targets. And this is what you need to prove. Because in the very definition of limits, here we use the letter epsilon, here we use the letter m. So students always wonder whether to start with an m or with an epsilon, arbitrary m or an arbitrary epsilon. What do you think? What should we start the proof with? An arbitrary epsilon or an arbitrary m?
Epsilon.
Great, right. And the confusion which you didn't fall into is sometimes students start with an arbitrary m. And that's meaning that you're trying to prove what is given to you. That's not good. We wish to prove that, so we start with an arbitrary area of 0. I'll write it in somewhere. Given an arbitrary area of 0, the limit 0, we need to prove that all but a finite number of elements of 1 over an are within said area. So that's what we need to do, and now let's look at how we do it using math. So given, so how do we measure an arbitrary area? By its radius. Given a positive epsilon, we need to find an k such that for all n larger than k, it is true that 1 over an minus 0 is less than epsilon. This in equation says the distance between 1 over a and the element of 1 over a and 0 is less than epsilon. That means the elements are within the area, like I said in words, human language above. Any questions so far? So now look at the analogy we did about the same with given sequences last time, right? So let's see here. That's a well, not the start. Oh, that's the time. So here, given epsilon, we need to find k such as for all n larger than k. 1 over the square root of n minus 1 is less than epsilon. That was when we were given a specific sequence. Now the sequence is more general, right? When I was given a specific sequence as a function of its index n, we always wish to single out n, to extract n. What do you suppose we wish to extract here? We obviously cannot extract n because an is not given as a function of n, right? Yeah, we wish to extract an. It's the closest approximation. And it also makes sense because I have some data about an. So yeah, exactly that's what's going to happen. Okay. So we will develop the inequality, and we have 1 over the absolute value of an needs to be smaller than epsilon. Agreed so far? Now I divide by epsilon and multiply by the absolute value of an. So 1 over epsilon needs to be smaller than the absolute value of an. So that is what I wish to be true from some point forward. All right. That is what we wish to be true from some index forward. And does that make sense to you given the data? Can you say that an in absolute value of an will be larger than 1 over epsilon? Why?
Tends to infinity.
Because exactly, that's the very definition here. Almost the very. The absolute value is a small problem which will pass. But the point is 1 over epsilon is some positive number. Since 1 over epsilon is a finite positive number. Doesn't really matter to any positive, to be honest, but let's just say. And an tends to infinity. There exists some k1, I would call it, such that for all n after k1.
הלו,
היי,
אתה בעיה במחשב? יש בעיה במחשב?
לא שידוע לי, לא.
אסור פה כי המחשב לא נדלק.
מתי? לא יודע.
מתי אתה פה?
אני... ממתי? מ-12.
אני יכול לעשות לדעתי את המחשב הזה?
המחשב דולק.
זה לא מנייד התגובה?
לא, זה המחשב הזה. זה המחשב הזה.
תודה.
עובד, תודה. Excuse me. So there exists some k1 such that for all n larger than k1, it is true. I always write it. It is true that an is larger than 1 over epsilon because it tends to infinity. So any given number, it will pass it forever. Agreed? Okay. But now it's important for me that it's positive. Since an is positive, what is the absolute value of an? The absolute value of an equals an, which is larger than 1 over epsilon. Agreed? So finally, we need to choose the k. Which k will we choose? Remember, each such proof has to have a step where you say, this is the k. Right, this is the main thing of all these proofs, because that's the techniques. That's the form of the proof. Given epsilon, I need to find k. Given epsilon, I need to find k. So sometimes I have to say that's why we choose k, or that's why we are able to choose k. So we need to choose such k, and which is that k?
The ceiling of 1 over epsilon plus 1.
No, not at all. That's the point. No, what you said works when the sequence is actually given and you're finding some functions of the index, but there are no function of the index here because it's a general sequence. What is the k here? The k here is the k1. So the k1 exists due to the limit of infinity, which is given. And what I'm saying, which is quite simple in this case, the very same point, the very same time, when an is larger than 1 over epsilon, 1 over an is smaller than epsilon, which makes sense, which is what we saw, right? So we choose k to be equal k1. And it's important that k1 is given to us by the data, and k is the one we need to choose. So, and so choose k to be k1 u ed.
Sorry, but Q1 was given as the point where
K1 is the point where an is larger than 1 over epsilon. And I'm sure that there is such a point in time and index because an tends to infinity.
Yes.
And I'm saying at the very same moment when an is larger than 1 over epsilon, that's the moment where 1 over an is smaller than epsilon, which is algebraically obvious, right? These are these two steps here. So it's easy. Not always do we choose the k to equal the k1. Sometimes it will be a bit more complex, but here it's not that complex. The connection is linear between the two. Okay. So that was the first proof. And I think I said it and I say it again. We need to try to follow these proofs, even though it's hard. We'll do many of them. And with each one, the understanding of the limits, the picture of the definition of the limit will become clearer and clearer. Okay, that's the first one. It's the hardest one.
the log for the calculus will be more each time.
The what?
The log.
The log, the hate, but not yet. Once you get to know a person, you either love them or hate them. It depends on the person, right? Okay, but you will get to know calculus better, that's for sure. Whether you love him or not, that's where you decide. Her, I mean, you probably think it's a her, I don't know. Okay. Yes. Okay,
Arbitrary heroes.
yes. And so, question. The other way around, given that an tends to 0, is it true that 1 over an tends to infinity?
I want to say yes, but there's a trick here.
Yes.
No. That's one of the things that even though I say each lecture, each year, each semester, and even if I teach calculus to few students, it's at each of my class, many times, people still fall at the test on this, and I will tell you why. And suppose, not suppose, suppose and the limits as x, I'm going to functions because that's where it is was about to say users, but students make mistakes. And suppose x, when x tends to, I don't know, x0, the limit of f of x is 0, okay? And I'll give you, for instance, for you to know about it, to think about it. For instance, the limit as x tends to 0. And sine x squared, or I'm changing it, just a second, I find a brilliant idea. Cosine of x squared minus 1. And that's 0 anyway, do you agree? Cosine of 0 is 1, 1 minus 1 is 0, okay? And now get something such as what is the limit as x tends to 0 of let's keep it easy for the now. Square minus 1. What would be the limit here? You obviously listened very hard. So you say 1 over 0, right? Infinity. Let's drop this function. Does anyone, by the way, have another guess before I?
Minus one.
Yeah.
The what?
Minus one.
Minus 1? No.
No.
Eventually something that's to 0 and that's it, like.
So let's look at it. 1 over cosine of x squared minus 1. So first of all, it's not an infinity by a long shot, right? It's not even there. It's minus infinity, exactly. Yeah, and that's the main point. It's either infinity or minus infinity. So students say, oh, but it's the same. It's not the same. It's super important. It's super important.
That's plus minus infinity.
But it is super important because if you're not sure it's one or the other, suppose it was e to the power of that thing. So e to infinity is infinity, e to negative infinity is 0. It could have large effects on the whole problem you are researching. Okay, and after you've seen the graph, you can look back at the function, I think, and understand why. Why is this negative infinity?
You're also going to graph the normal function, like not the inverse, just the cosine of x squared minus 1.
I don't need to graph it. You can do it in your head. Why is it true? What are the values of cosine?
From minus 1.
And you subtract 1. It's negative. It's negative. That's all. You don't even need to know the graph. That's what I meant. And you need to know that this is the. So I'll write here a 1 over 0, but 0 cannot be negative or positive, right? But this sign means it's 1 over 0 coming from the negative side, which means the function tends to 0, but it is on the negative side, and that will be minus infinity. Yeah, but this is not computer science, this is actual science. So yeah, we always laugh that you don't say math science, physics science, because it's obviously a science. You do say computer science. Sorry.
Yeah, the science is ironic.
Yeah, okay.
So we cannot understand a over n tends to 0 from minus or from plus, and we cannot say it's will be
Yeah.
infinity or minus.
Or another case, if it's actually equal to 0.
Yeah,
So then it's not defined altogether. So I will make a theorem out of all of this thing, but it's most important for me, for you to remember that 1/0, excuse me, reminds us. I'll write it and then I'll answer some questions. Remember when meeting 1/0, one must ask the sign of the sequence or function. And it could be plus or minus infinity. I think that's the main point. That's why I've shown you functions. Functions are not due to until this third part of this course, but that's where sometimes it takes too long and students forget this simple but important rule. Yes.
What's the limit if we go to that one?
What? Because cosine of 0 is 1, 1/1 is 1. Then there is no problem at all. Yeah. Okay, so now the theorem, the actual theorem. When I go Italy, my neck always stands. Sorry. Assume AM tends to 0 and does not equal to 0. So I have a sequence of numbers whose limit is 0, but none of the elements are actually 0. Then 1 over this absolute value of an tends to infinity. That is true.
yeah.
Agreed?
So you could say in general that if it's 1/n, it tends to positive or negative infinity. Or
No, because it might interchange the sign.
Okay.
And what is most interesting mathematically, I'm using this word loosely. What is the main mathematical point here is why proofs has to be so exact. If I write here an, then the theorem is false.
Yeah.
So it must be that somewhere along the proof, I use the fact that the absolute value here, and if it wasn't there, the proof will not work. So when proving this, I will show you. I will show you when I use the absolute value in the statement of the theorem. Okay? So again, we are given data and we need to prove some target. The data now is that an tends to 0 and it's different than 0. And this is what we need to prove. So I'm looking at eyes on the prize, I'm looking at the target, I need to prove that. So I'm taking an arbitrary M, which is an arbitrary area of infinity. Given M, now writing words for an arbitrary area of infinity, we must choose K such that for all n after K, it is true that, let's see if anyone here can finish this sentence. What we wish that will happen after a while.
there's a ray.
The ray is there. What is the final inequality?
1 over
1 over the absolute value of an
is so it's here, okay.
it's not k, k is the index, right? It's not there.
M
Bigger than
M.
m. Exactly. Okay, see, it's confusing, but after you do it for a while, you start to put all the pieces together. But in order to claim that 1 over an tends to infinity, I wish to say, indeed, 1 over n is larger than an arbitrary number someone chose for me. If someone chose the arbitrary number, the sequence is indeed above it when all parts for all but a finite amount of numbers, which elements of the sequence, which is this k. K is the number of elements outside. The rest of the elements are inside. Okay. So that is what I need. And here, we wish to extract an as before. So what will we do? We multiply by an and we divide by n. So develop. And we get that 1 over m must be larger than the absolute value of an. Agreed? Note, we use here the fact that absolute value of an is positive if the inequation 1 over an without the absolute value, the next step would not have worked. And it wouldn't work not because we didn't solve it, but because it's false. If an is negative, 1 over n will not be larger than n. It will be, in fact, smaller than n, because it actually tends to negative infinity, right, rather than infinity itself. Okay, so that's what I said before. Within the proof, the exact statement of the theorems is used. So, do you think that the absolute value of an will actually be smaller than 1 over m?
an turns to 0.
Yes, because an tends to 0.
Yeah.
So 1 over m, think of it as the radius of an area around 0, from negative 1 over m to plus 1 over m. And yes, an is definitely supposed to be there because it's some area of 0 and an tends to 0, so it will be there in perpetuity apart from finite number of elements. So what I actually write from all this, I write since an tends to 0 and there exists some k1 such that for all n after k1 it is true that the distance between an and 0 is smaller than the arbitrary number, positive number 1 over m. And here I could have chosen any positive number because this definition is known for me. I know that for every area it will be there, so I can choose any radius I like, and I'm sure that it works. That's the difference between the data that is given and the target which needs to be proven. So when I need to prove something, I assume it's arbitrary. And just like in computer science, the parameter you get from the user is arbitrary. You cannot assume that it is not malignant or malicious, and but the variable you return, you can return whatever you want, so something like that. And finally choose K to be K1 and that's exactly what we needed. We needed the absolute value of AN to be smaller than 1 over M. The very definition gives this to us on a silver plate. Any questions so far? Yes.
So this is like applying the same formula you did before, AN is just the term, 0 is the limit, and then
Yes.
it's
Yes,
some over M.
and it's general because you don't know actually what is the term. You don't know what is the actual sequence, so you use only the definitions, and that's exactly why you need the definition in order to prove general theorems. Once you have a specific sequence with a specific definition of the elements of the function of the index, you usually don't use the definition at all. You use the theorems themselves. Okay. Let's think about the next one. Definition. We say that the sequence AN is bounded if the set of elements of the AN such that N is a natural number is bounded from above and below. Same bounded, I mean, from above and below. Samil El and Samil and claim AN is bounded if and only if there exists some positive M such that for all and in N the absolute value of AN is smaller than N. I'm leaving this claim for you as an exercise for home, and it's simply very useful. I will do one small example that will convince you that it's true. It's not a whole proof, but I'm just happy if you will be convinced that it's true. So I'll write explanation. And in general, when I write an explanation, it means it's not a full proof. Okay? So if AN in absolute value is smaller than M, then AN is bounded between minus M and N. Do you agree about this way? This is actually the proof in this case. The other one is the one that I will give you an example rather than proof. What happens if AN is between -7 and 3? What can you say about the absolute value of AN?
That it is between -7 and 7, like it's less than 7.
Less than 7, exactly. So the only difference between this and a full proof is writing A, B, and take the maximum of the absolute values of A and B. But I think actually seeing it in your eyes is even better than an actual proof, because you understand the meaning of the theorem, right? You take it doesn't mean that, it doesn't matter if it's positive or negative, you take the longest distance from zero, and that's the absolute value. Yes, Sam,
So,
you just wanted to raise your hand.
no,
No,
yeah,
yeah.
that's-
I
just what he said.
Just that? Yeah.
Um, I don't know. Why can't we say, oh, it just seems a bit like oversimplified.
But it's true, are you convinced it's true?
It's true.
So
the
the-
bounds of
you can- wait.
AN is -7 and 3.
Yes, so you say it's less data than you originally had, right?
Yeah.
And you are correct, but I don't need all the data, I need to finish my proofs in the easiest, fastest way possible. And usually saying it's smaller than some number is enough, because it's usually some number versus infinity. And then you say, I don't care what are the numbers. Okay, that's the thing. Sometimes, especially by the way, in computer science, you actually look for the tightest bound because they tell you something about the complexity. Great, but here in general proofs, usually it's enough that there is some number, and it's very good for us to work with absolute value because it's positive, and then within the inequalities, it makes the algebra that much easier. So you're right that this is less data, but it's easier to work with, and sometimes we do it. Sometimes we cross out data in order to get a somewhat harder question, harder problem, but with easier solution, right? If I can show that a number is smaller than 9, then it's definitely smaller than 200. So in some sense, it's a harder problem, but many times it's much easier for me to actually prove that it's smaller than 9. I don't have an example right now, but we'll see if you
But
like.
all practical terms.
Yeah, yeah, yeah.
With actual calculation.
Yeah.
Right on.
Not calculation, proofs. For
Yes,
calculation.
the-
No,
the-
sometimes,
Okay.
sometimes for calculation, but usually for proofs,
Okay.
usually for proofs.
Can I ask you a question on top of that then? If you
Yes.
had square brackets, there was,
Including, yes, yes.
then would Rm be 8?
Yeah, anything larger than 7, yeah. 7 point something. Okay, yes. So, theorem is the sequence AN tend to a finite limit greater than infinity, then AN is bounded. Makes sense? But still the proof is one of the first in the course, it's rather challenging. It's not challenging, it's hard to understand. Proof. And well, it is challenging to write yourself, and it's a bit hard to understand. But I think later on in the course, when you look back, it's quite easy.
That's already.
Yes. If you get to the end of the course, that's that's the problem. Okay. So I'll let you try for a bit. I know that I have a sequence. The sequence is converging. I didn't write this word. I wish to do it. Notes. If the sequence AN has a finite limit, we say it converges. Okay, so the theorem says that if AN converges, then it's bounded. Okay.
So if you make an area around the limit, you make the area have an epsilon that has all the points, then the epsilon
Well,
is,
there is no part definition that allows you to demand all of the points to be within the area. Right? The definition always promises you that all but a finite amount will be in the area.
okay.
Which epsilon would you choose? I think that's one of the things, we need to choose an epsilon, but it doesn't matter which one we choose, but we need to choose.
Because
Choose epsilon equals 1. It's an arbitrary choice, any choice would have worked. Oops, not an apostrophe, 1. And there exists a k such that for all n larger than k, it is true that n would be between L minus 1 and L plus 1. Agreed? So most of the elements are bounded, but there are supposedly k elements outside of these bounds. Agreed? What can you say about these k elements? Can they make the sequence unbounded? Why not?
Because
It's a bit of discrete mathematics, but not sure that you said a specific thing.
You asked that one time.
What?
You asked the question.
Can the k elements that are outside of these bounds make the entire sequence unbounded? Right? Because if all of the elements of the sequence were within this bound, then it's obviously bounded by L plus 1 and L minus 1.
Yeah,
That's-
no, because we can just choose another epsilon, right?
So there are other bounds, doesn't matter.
yeah,
Having one bound is enough, right? If it's smaller than L plus 1, it might be also smaller than L plus and a half, I don't know. Definitely from L plus L. That's not a problem. What we've shown here is 99% of what we need to show. Almost all of the elements of the sequence are bounded between L minus 1 and L plus 1. The problem is this finite amount of numbers up until k. What can they make this sequence unbounded?
so we have most of elements bounded, but in the sequence, there is elements that are not bounded, and so sequences cannot be bounded at all. Like,
You're saying my theorem is false.
but it sounds like that.
because R is.
3 elements. Could two elements? Could 2 elements make a sequence unbounded?
No, because of.
Why not?
Because
Why
of
not?
R,
Can one element?
Why not?
How can an element make the sequence unbounded?
Uh,
What number makes it unbounded?
there's.
A million?
I don't know.
The powers.
No, you do know.
Eh,
It's one number. One number cannot make it unbounded because one number is a finite number. It's in itself could be its bound. It could be the largest, right? It could be that the number outside of this area is huge. It's a million. So he is the bound. Every finite amount of elements has a maximal one and a minimal one. That's why I say it's discrete mathematics. If you have an infinite set of numbers, that could be unbounded, like 1, 2, 3, 4, 5, 6, it keeps going up, unbounded. But every finite set of numbers has a maximal of 1 and a minimal 1, and that's why it's bounded.
In R.
Yes, numbers are always finite, there is no number infinity, so yeah. Well, I'll try to write it up in some way, and this just like I said, it's simple, but it's hard to
And because of
Entertainment.
because of the qualities of the real numbers, there's always a bigger number than one number. Like every number has a bigger number or a smaller number, and a smaller number, so.
Yeah. So the sets. Right. And the set of elements AN. Is the union of two sets. First of all of the elements up until the K1. And then all of the elements after K. So this part is bounded because we've just seen. Right, this part is bounded between L minus 1 and L plus 1. This part is bounded because it's finite. Bounded because of finite. So the entire set of elements is the union between two bounded sets and therefore is bounded. The union of two bounded sets is bounded by the maximal bound of them both. Not true for an infinite set of sets, but for two, just two, the bound is just the maximal of the two. It could be that the bound is between these first elements, and it could be that the bound is actually here and all the elements are and there are a few examples. I wish to elaborate on that. Any questions so far? Yes.
The thing the set on the right is bounded because of what we just written about.
And answer on the right.
That is bounded because of what we just.
Yes, because we said for all n larger than k, an is between these two bounds. So one can write Chasami L for this set is L plus 1, Chasami La is L minus 1, the upper bound and the lower bound. Okay, they are just written here. You don't have to be supermoon, but I don't care. It's just that we need to have any bound. Okay, these are the examples I didn't wish to elaborate about. And okay, so let's it is like I said, I like to work through it so you know it and make sure I'm not skipping anything. So we've proven this proposition and we've proven this proposition. I skipped this and I will mention it in a bit. And we've proven this proposition. סדרה המתכנסת לגבול סופי חסומה. Okay. Again, I urge you to try to read this in order to get your Hebrew together. Like I asked you in the first day of the course, you will need later to be able to speak Hebrew with these concepts. So I think it will help you. This one I haven't got to yet, and then okay. This one is nice. Maybe I'll do this one next. Okay. This one is I forgot to do a short video about, and then I added it later. So this one is the only one that doesn't have a proof on video here. So I usually do it in class now. So let's do it. Okay. And proposition. Given a number A a sequence an such that for all n, I don't like my phrasing. Given a such that for all n in wait a second, given a number a and sequence, sorry, and a sequence a and such that I think that's okay. Given a in R and a sequence a n such that for all n in n, it is true that a n is smaller or equal to a. Also assume a n converges, i.e. there exists some limit such that a n tends to this limit. Okay, so now look at it. I used many words. Really in Hebrew I use less words, but I'm not sure why. In any case, I didn't say a lot. We have a sequence again. All of those elements are smaller or equal to some given number a, and we know that an converges to some limits. What would you say the connection between the limit L and the number a?
L is smaller or equal to A.
Yes. Note, an important note. If an was always smaller, strictly smaller than a, then what would you say about L?
Same,
What?
same.
What do you mean same?
No,
It's
it's
the same thing.
no, it's
It still be L is smaller than today.
no, it's equal to A.
It could be equal to a.
Yeah.
Okay, and that's why I've written it here. Look, I've written it here that if an is strictly larger than a, then the limit is larger or equal to a. And then always students ask me, why do you demand it to be strictly larger than a? If it's equal, it's still true. In order to get this confusion out of the way. And many times students make this mistake, they say that the sequence is smaller than one, therefore the limit is smaller than one. That's not true at all. It could be that the sequence of numbers that are smaller than one tends to one, and the limit is actually one. Okay, so it's rather important. And so I wrote it in big letters. But the proposition itself, I will prove in a few seconds. Any questions so far? Again, what you see we do is write general theorems and prove them using the definition. Later on, when we do calculation, we can use all of them. You will see almost any theorem here you use at least once in some kind of exercise. Say, for instance, there is such an exercise in which we can say that the limits could be either a bunch of numbers. Then you say, oh, but because the sequence are all positive numbers, it couldn't be that the limit is negative, and then you finish the exercise. That uses this proposition. So, proof. And ABC assume by contradiction, nabash in Hebrew, and I'll write again there. Assume by contradiction that L is larger than A. Let me draw it out for you for a second. So. This is A. Where are the elements of the sequence? To the left. Right? Where did we just assume L to be? To the right. Color. That's nice. That's it. Okay. Does this drawing make sense? Because the element, I didn't write it, I'm sorry, I'll do it in a second. And. Does it make sense that the sequence tends to the limit L? But all the elements of AN are smaller than A.
Let's say.
But the contradiction is, our assumption is that AN equals to L, and L is larger than A. Does that make sense?
No.
No, and we need to say why it doesn't make sense. He said, as always, when we assume by contradiction, we get an inexcusable drawing, right? An impossible drawing. It doesn't make sense. But the question is, how do we prove that it doesn't make sense?
I have an idea, but I
Yes.
don't know.
Try.
The thing that I would say is that there exists a point which isn't there where you can have a for all sigma that there's a infinite amount of points inside and a finite amount outside, but you can't say there's a point and not declare where's the point, right?
Yeah, but not a point, an area of an L.
Yeah,
It's an area.
it's an area, but it's not in L because that's the contradiction.
No, you take an area of L. No, you take an area of L. Sam, you wish to say something?
Yeah, I was gonna tell us what you're saying is right.
No, what I'm saying is right, but what I'm saying is that because I don't have like which point it is, because it's L usually, but here L is not the point because we.
Which area of L should I take?
A plus L over two.
The minimum of AN,
No, you're thinking about the sequence, you shouldn't. I'll take such an area which starts with A and end here, alright?
yeah,
And then I'm saying this area of L must, yeah, the epsilon would be L minus A, exactly. Yes, L minus A. And it's positive because L is larger than A. So I'm taking an area of L who has 0 of the elements of the sequence. And that's a contradiction to L being its limit, because it must have all of them apart from a finite number. It has none of them. Okay? Now that's why I do the drawing. They help us understand the algebra which we write in the proof. Okay? So, write epsilon to be L minus A, which is positive by our assumption. And therefore, in the epsilon area of L, there are no elements of the sequence since AN is smaller than A, which is L minus epsilon. Right, L minus epsilon is exactly A, which contradicts the fact that AN tends to L. Right, if it was actually the limit, then in every area, large and small, all of the elements will be there, apart from a finite amount. And in this specific area, it does not have.
Can we actually draw pictures for this?
But I don't use the picture in the proof. That's what you need to. So you can draw whatever you like, but you need to write sentences afterward, right? So one, if it was a book, I don't know, maybe or some lecturers do it. They will just write only these sentences and see. Here it works, but they don't explain how do I thought about this epsilon and why did I do all I did. So that's why I'm adding the drawing for you to understand that you're still required to be able to write it formally, not just this drawing does not make sense. Like geometry in high school, you couldn't just draw up a triangle and say, you see, it's both I don't remember the names in English. Not the Tichon. And perpendicular and how do you say Tichon? Tichon is
High
the
school or?
no.
Uh,
Within a triangle, the line that goes to the middle part of the
The Middle East.
the Middle East, yeah, Tichon. It's from the same. Tichon is middle, and yes, it's from the same root, but whatever. In any case, the drawing is not. Okay. And next, proposition. Prop. And given a sequence AM and given two numbers L1 and L2. If A1 AM tends to L1 and also AM tends to L2, then what does it mean? Does that make sense that a certain sequence has two limits?
If L1 equals to L2, so yeah.
Then L1 equals L2. That means that a sequence could not have two different limits. And I will leave you this one as an exercise.
What are there? These are two sides that's bounded.
It won't be, none of them would be the limits. Take the sequence -1 to the power of n, which is -1, 1, -1, 1. It doesn't have any limit. Couldn't have two limits because all of the elements should be in the area. And this is, by the way you prove it. You take two disjoint areas of L1 and L2, and the limits, the sequence ought to be in both of them, which is impossible. Okay, so I'll give you this one as an exercise, and another one which is very important. And proposition. And given sequence AM and number L, then AM tends to L if and only if AN plus 1 tends to L. And this theorem is quite important, but one needs to understand what does it even mean. So what does that even mean? So I'll give you it's not example explanation. Say the elements of AN are, what is the first element of the sequence AN?
A1,
A1,
Yeah.
A2, A3, and so forth. Agreed?
Mhm.
The elements of AN plus 1, what are those?
All of them plus A and plus one.
A2,
No.
A3, A4.
Are A2,
So it's just the sequence.
A3,
Yeah,
A4,
okay.
right?
Ah,
Because
yeah.
if you substitute n equals 1, then you start with A2. Agreed? So the difference, so and difference of one element does not affect the limits. Does that make sense? If you have an infinite sequence, I change one element, I deleted one element, it doesn't change the limit. And the same goes for any finite change for any change in finite amount of elements. Changing a finite amount of elements of the sequence will not affect the limit at all. That's what this proposition basically tells us. And again, I will leave it as an exercise. And that's not true. Exercise. I would just say that the main reason is that in order to for the definition of a limit to hold, you need the elements to be within the area from a certain point forward. So if you change a finite amount, it doesn't change the basic fact that from some point forward it will work. The k might be +1 or -1. That's the main thing here. Again, the proof that I leave that exercise are on the video. You can watch them in Hebrew and see the full proof. And some I prove, some I leave as exercises. Any questions so far?
Is it worth saying a positive finite change? I mean,
No, it's an amount. Amount is always positive.
not sure.
Because that an amount, finite amount, it's not the size of the elements, it's the amount of the elements, which is a natural number, right? Rather than changing all the elements in the odd indice. So that's changing an infinite amount of elements, that's obviously could change affect the limit. But any natural number is a finite amount. You don't need to go positive or negative. Okay. I don't wish to go to the next step yet, and we have only 5 minutes, but I wish to show you an example for calculation because we did a lot of proofs today. Example. Calculations. What is the limit of the square root of n squared plus 1 minus n?
Okay, of square root.
care to venture to guess? Why?
Let's just
I'll hint. I'll hint. Who is bigger? N squared or one? N squared, right? That goes to infinity. So does this one makes a lot of change?
no.
No. What would happen if this one was stricken off?
And understand zero.
Is zero, right? And I just would want to say that the purpose of this example is that you are not allowed to do this, right? But I help you with your feathers, yes. Okay. So next, what I didn't solve it yet. What is the limit of n squared plus n plus 1 minus n? So by the same sense, you say, who is bigger? Let's say n is 1,000. So that's 1,000,000 and that's 1,000, right?
Yeah.
You would say both n and 1 are negligible. Let's
Yeah.
strike them off and we get 0 again, right? And so let's just see. From
And we are like. Sort of a fan.
square root of 1,000 squared plus 1 minus 1,000. What is that close to? 0, right? That's what you guessed. But now let's put in here plus 1,000, which seems negligible. Agreed?
It's meant to be.
Yes.
Then.
So now we see.
I mean, still not the.
If we will get the.
But what does it look like?
Uh-huh.
Which is actually the right answer,
Yeah,
right? And my point is, all right,
do not do this.
yes, exactly. It's things that seems negligible to you might not be negligible. I didn't prove why is that half, and I didn't prove why is that 0. And that's another thing I wish to convince you that I didn't solve any of them, right?
Yeah.
Okay. And that is surprising because if we try out n plus 1 as negligible. Negligible, and we will get 0 at both cases, but we will be wrong. Many times students neglect things and then I mark points, so I say, but I got to the correct answer, yeah, by mistake. It's not a valid way because sometimes it doesn't work. And next session we will start from this example and we actually calculate it. It's not that hard. I don't have enough time to calculate it, but it's not that hard. It's algebraically quite easy. But I hope I managed to get the point across. Good day, see you in Tuesday.
Yeah.
It's usually the last section.
Yeah.
So.
Did any of you on linear algebra got a mail that I'm canceling linear as well?
Yeah.
You got two mail?
No,
we only got one.
Yeah, so I forgot.
I think that's obvious.
Yeah. No, but there is at least one student there. Yeah.
So that next Tuesday, we don't have any lessons.
Yes. Yeah, because I will be brilliant.
So you'll be in England?
Yeah.
Someone said in England.
My sister is from Glasgow, so I'm flying out to Heathrow, and then I take a train to Glasgow.
Enjoy the sunny weather.
I have enough sunny weather here, it's
Yeah.
fine. It's fine. Although I am moving Lord of the Rings now. And there's a certain part when a cloud from Mordor eclipses the sun. I say, oh, it's a cloud. I get it.
Finally, they ended up making the movie in New Zealand.
Yes.
Enjoy the.
Bye.